Assalamu alaikum, sir. I am Abdullah Nafi. Here, along with my teammate SM Tasin Zaman and MD Shakil Ahmed, we like to present our project for CAC 754. Our project title is Explainable Transfer Learning for Multi-Level Chest X-ray Diseases Classification. In simple word, we build a deep learning system that can look at the chest X-ray images and tell us which disease is present. Not just one, possibly multiple diseases at the same time. And more importantly, we made it explainable. That means the system can also show why it made a particular prediction, which is the part of X-ray it was looking at. Next slide, please. Here is a quick overview of what we will cover here. So let's start it. Next slide. Let's talk about why the problems matter. Chest X-rays are the most widely used medical imaging tool for detecting diseases in the lungs area and chest area. They are fast, cheap, and available almost everywhere. But interpreting or classifying them correctly is not easy. It requires expert radiologist, and even accurate diagnosis is critical for a patient treatment and recovery. Now the challenge is the real-world X-rays are complex. A single X-ray can show sign of multiple diseases at the same time. For example, a patient might have both pneumonia and pleural effusion together. This is called multi-level problem. That means one image and multiple levels. On top of that, there are several classes imbalance. Some diseases appear very frequently in the dataset, which others are extremely rare. This makes it harder for models to learn rare diseases well. This is exactly what are we addressing. We use a benchmark dataset called MedNest version 2, specifically the ChestNext subset, which is a large-scale and standardized collection of chest X-ray images. It allows fair comparison and productive experiment. So our goal is build a model that can both accurate and explainable. Next slide, please. Before building our system, we reviewed the key research paper in this area. So let me quick through highlight the six most important paper we read. The first paper introduced MedNest version 2, the benchmark dataset we use, which is enable the standardized evolution of multi-X-ray classifiers. The second paper released the chest X-ray Ray 8 dataset, which is over 112,000 X-ray images with 14 disease levels, and also highlighted the need of model that can both classify and locate it into the image. The third paper shows that adding GradCam to DenseNet pipeline is significantly improved and how well a doctor can understand and trust the model without hurting the accuracy. The fourth paper introduced AssembleNet, which is a combined heat maps for multiple level models to produce better and more reliable uh, localization better than a single model. The fifth paper show the ChestXNext model that deep learning can match a radiologist level performance on 10 out of 14 diseases. Prove that AI has a real clinical potential, but also the transparency is needed. And the last paper proposed a transfer learning framework which use multi-level lens classifier classification. Together, all the six papers support our three main choices are multi-level classification, explainable through GradCam and AssembleCam, and evaluation on a large scale of dataset. Next slide, please. Now let me describe the dataset we use. We use MedNest version 2 ChestNest dataset, which is a large-scale and standardized benchmark for chest X-ray classifications covering 14 diseases. The image are chest X-ray in grayscale PNG format. Standardized is to a size of 224x 224 pixel. Each image have multiple disease level, making the true multi-level classifier problem. The dataset is split into three parts: training set, evaluation set, and test set. So combined total nearly 1,000 images from over 51,000 patients. The key strength of this dataset is its probably is publicly available and consistently level with expert verification and ideal for developing explainable multi-level models. Through class imbalance is a real challenge which is we'll discuss next. Next slide, please. To understand our data set better, we did a data analysis. Looking at the level distribution, we can clearly see the imbalance. The top three most common diseases are, uh, are account for a huge portion of all level. Meanwhile, the real classes like hernia appears in only 0.18% of images, and and the majority classes are roughly 100 times more sample than the rarest one. These kinds of imbalance is a serious problem. If we train without handling it, the model will just learn to predict the common diseases well and completely ignore the rare one. To fix this, we computed positive class weight, which tells the model to pay more attention to the unrepresented classes during training. For example, hernia and mass get the maximum weight of 20, while infiltration get only 6.64 because it's already common. To provide a clear understanding of the framework and the procedure we imply, I will hand over to my teammate MD Shakil Ahmed to walk through the methodology. Shakil.
Thank you, Nafi. I'll continue from here. The total workflow of this experiment segmented into 8 parts, from data preprocessing to inference. After preprocessing the dataset, split into 3 ways: training, testing, and validation. The trained data was augmented for better generalization with base model ResNet 18 and primary model DenseNet 121 trained on this data. Since each data points may contain multiple levels, we need to consider binary classification for each level. Next slide, I will provide details on training setup and model training. Evaluation, inference, and rest will be done by the group member. Experiment setup and training details. Here we focus on the experimental setup and details on training configuration for our XTRM multi-level classification tools. We ran all experiments on Google Colab using NVIDIA Tesla T4 GPUs through a cloud-based GPU pipeline. This ensures consistent computation and reproducibility. Our optimizer is AdamW, and the loss function is binary cross-entropy loss with logic loss. Suitable for multi-level classification, we set maximum epochs to 25 with a batch size of 32, where TK is 10 to the power minus 4. For regularization, we used early stopping and patience of 4 epochs. Finally, we trained the workflow is data loading and preprocessing, transfer learning model setup, phase 1, backbone freeze warm-up, phase 2, full fine-tuning, and the last, validation-based model selection and test evaluation. Finally, our explainability, we use GradCam and EnsembleCam. This uniqueness of the ScambleCam is here. We take last 5 convolution layer is where the traditional approach to take different weak model and aggregate them. Our approach shows significant upward performance when we cross-check with other approaches. Heatmap produced by this method highlight the important region of the image that influence the decision of the classifier. For example, if a patient has pneumonia, it will highlight the opaque region of the image to indicate lung infection. That's all from me. Hassan will continue the rest.
Thank you, Shakil. Now I will present the final results of our 2 models. We compare ResNet as our base model and DesNet 121 as our primary model on the ChestNet test set. From the table, DenseNet 121 performs better than ResNet it in across the main evaluation metrics. It achieves higher micro F1, macro F1, micro AUC, and macro AUC. Since this is a multi-level classification problem, AUC and F1 score are especially important because we need to evaluate performance across multiple disease levels, not just overall accuracy. The model ranking also shows that DenseNet 121 achieved the best overall score, so we selected DenseNet 121 as our final model for explainability analysis. Next slide. This slide shows the per class performance of DenseNet 121. Since chess means contain 14 disease level, we need to evaluate only the not only average performance but also how good the model performs on individual classes. The top section shows the class with highest AUC like hernia, emphysema, cardiomegaly, and etc. And effusion have stronger class level performance. The lower section show weaker class such as infiltration and nodule, where module had lower AUC values. This shows that model don't perform equally across all diseases. Some classes are easier to distinguish visually, while others are challenging because of class imbalance, subtle visual patterns, or overlapping disease features. The ROC curve also supports this point because some disease classes have stronger separability while others are hard to classify. Next slide. This next slide. This slide presents the explainability results. After selecting DenseNet 121 as the final model, we applied GradCam and EnsembleCam to understand which part of the chest X-ray influenced the model's prediction. GradCam produces heat map that highlight the important region for predicted class. EnsembleCam can extend this idea by combining information from multiple convolution layers, giving a more robust explanation than relying on a single layer. In the examples here, the heat maps are overlaid on the chest X-ray images. The highlighted regions show where the model focused when making the predictions. This helps reduce the black box nature of deep learning and makes the model's behavior more interpretable. This slide also includes a quantitative XAI summary. This helps us compare how different classes respond to the explainability method and whether the highlighted regions are meaningful. Next slide. This next slide. This slide also summarizes the main analysis. Architecturally, DenseNet 121 performed better because dense connections help reuse feature across layers, which is useful for medical features where subtle patterns can matter. DenseNet gave stronger results, and the XAI output showed possible focus regions. However, class imbalance and subtle disease patterns remain limitations, so the model should be treated as a support tool rather than a replacement for doctors. The XI validation section also shows that the model's highlighted regions are clinically plausible. The GradCam and EnsembleCam examples indicate that the model often focuses on relevant anatomical areas instead of random background regions. The dataset clearly has a class imbalance, as some disease levels are visually subtle and some classes have lower performance. This means the model should not be treated as replacement for clinicians. It should be viewed as a decision support tool. Next slide. In conclusion, DenseNet 121 was the best performing model. The GradCam plus EnsembleCam helped make its predictions more interpretable. We trained and compared both models, and DenseNet had better performance. The GradCam and EnsembleCam was applied to make models predictions transparent. The visual explanations show which image regions influence the predictions, and confidence drop analysis helped validate these highlighted regions were meaningful. Future improvement could include using uh, overall the project also showed that the transfer learning can be effective for chess means classification, and explainability methods can improve interpretability and trust in medical AI system. Future improvements could also include using larger and more diverse dataset, testing on real clinical data, improving on low performing classes, and validating the model with medical experts. Next slide. This slide lists the main papers and sources used in the project, including MedMinst V2, Chest X-ray 8, GradCam, EnsembleCam, DenseNet, ResNet, and other related explainable AI studies. Final slide. Um, Thank you. This concludes our presentation, and thank you for listening. Thank and watching our presentation. Thank you.
Thank you, Nafi. We will start the demonstration now. Nafi, would you please start the demonstration?
Thank you, Shakil. In the first cell, we set up our environment. We are working in Google Colab. So before everything else, we install Midnest, the library that gives us all the access of ChessNest dataset. Library like PyTorch, Torch Vision, and Scikit-learn, Matplotlib, all are already available in Colab, but we will make sure everything is placed there. So we can say the cell is the foundation that every other cell is depend on. In cell 2, the cell does two critical things. First, it set a random seed of 42 across, so our result could reproducible across run. Second, it defines all the experiment settings in one place. Settings like image size, batch size, training epochs, and the learning rate, and early stopping with a patience of 4 epochs. We also mount it to the Google Drive here, so all the models, figures, and tables are saved permanently. In the next cell 3, here we load the dataset using Mednest info dictionary. ChessNest is a multi-level task, meaning a single X-ray can have 0 on multi-level disease level simultaneously. In this dataset, there are 14 diseases level in total, and we also use binary cross entropy loss, not softmax. And in next cell, please. In cell 4, ChessNest images are grayscale, but our pretend model expected a 3-channel RGB input, so we convert each images by repeating the grayscale channel 3 times. We resize we resize to 224 into 224 pixel, applying light um, augmentation during training, a horizon flip and a small rotation, and normalizing using ImageNet means and standard derivation. In cell 5, before we building the model, we always inspect the data. The cell shows us exact X-ray images where training sets are with their disease level. The bar chart below, it reveals something important. The level distribution is highly imbalanced, and common findings like infiltration and effusion appears far more often than rare one like hernia. This imbalance directly motivate to class weighting strategy we apply into the next cell. In cell 6, because each of the 14 level is independent yes or no decision, we use binary cross entropy with logic. To handle class imbalance, we compute a pose weight for each level, the ratio of the negative and the positive sample are kept it to 20. This means the model is more heavy for missing a rare positive level. You can see here the weight printed for each diseases. Real level like a hernia gets a much better higher weight than the most common one. And the cell 7 will explain by Shakil.
Thank you, Nafi. Again, in cell 7, the main theme here, we build two models, ResNet 18 and DenseNet 121. For both of the model, we place the final layer with 14 multi-level classifier based on our dataset. In cell 8, for multi-level classification, single matrix is not enough to measure performance, especially in multi-imbalanced dataset. So we choose a wide range of matrices from level-wise accuracy, F1, recall, AURAC, and so on. In cell 9, this is the heart of this operation. We are setting up our training and validation loop of our model here. The total workflow can be divided into 3 parts. Forward pass, loss calculation, and backward pass. In forward pass, we send the image and get 14 losses. In the loss function, we calculate the loss by comparing with ground truth. And finally, we update our parameter by calculating the gradient of loss function with the respect of particular weights. Now cell 10. In cell 10, we started to training the base model ResNet 18. So we'll go to the result part directly with this thing. We can see in the result, the model is learning fast, but after around 7 to 8 epoch, the validation loss starts increasing while training loss keeps decreasing, which indicates overfitting. In the performance table here, the model achieves high overall level accuracy, but AUC shows that limited exact multi-level match and uneven per class precision. Recall indicating moderate multi-level generalization. In cell 11, now this is the time for training our primary model DenseNet 121. And if we go to the result section, there is also a overfitting tendency, while other matrices in the table shows that it's a promising result. In cell 12, this cell make a detailed comparison on the wide range of matrices for both of the models. We can see DenseNet 121 perform better than the base model. Both have overfitting tendency. We can see there are two curves side by side, and both of them are showing some sort of overfitting tendency. So next cell 13. In this cell, we do a per class performance analysis. And we can see the table here. The class-wise performance show a high AUC for the most of the levels, but very low precision and F1 for the rare classes like pneumonia, pleural, and fibrosis. In cell 14, this is the multi-level confusion matrix to get better understanding on the models, like the true positive, false positive, and negative, false negative, this thing will help us to understand the model, how it's performing, and what's the wrong with the model. That's the thing here. And lastly, in cell 15, in this cell, we try to analyze the performance using ROC curve. We can see here, the ROC curve shows that the model has a strong discriminative ability for cardiomegaly and effusion, while performance is lower for infiltration and nodules, indicating uneven per class prediction reliability. That's from me. Tasin will explain from the cell 16.
Thank you, Shakil. Now I will explain the explainability part of our project. After DenseNet 121 was selected as the final model, we applied GradCam and EnsembleCam to understand what regions of chest X-ray influence the model's prediction. GradCam highlight the important images for a target class by using uh, gradients from the model convolutional layers. Ensemble Cam extends this by combining information from multiple later convolution layers, so it can provide a broader explanation of the model's focus. Since this is a medical imaging task, explainability is important because we don't want only want predictions. We also want to understand what visual region influence those prediction. Uh, in cell 17, we see the visual GradCam and ensemble cam. In this section, we visualize the GradCam and ensemble cam heat maps on chest and amnesty test images. Each visualization help us see whether the model is focusing on relevant chest regions when focusing on predicting a disease level. When we look at these examples, the original chest X-ray is shown along the heat map overlay. The brighter or more intense region represent areas that had stronger influence on the model predictions. The goal here is not to claim that heat map is medical diagnosis by itself, but to make the model's decision process more transparent. In section 18, we see the we sanity check the confidence drop. To further evaluate the explainability results, we used a confidence drop sanity check. The idea is that if a CAM method uh, uh, highlights truly important regions, then masking those regions should also reduce the model's predictions. In our final run, masking GradCam highlights regions reduced confidence by about 0.11 on average, while masking in SampleCam highlighted regions reduced confidence by about 0.070 on average. This suggests that both GradCam and EnsembleCam highlights regions that were meaningful to the model, and in this particular run, GradCam produced a slightly stronger confidence drop effect. In section 19, in cell 19 we see that the clinical interpretation template. Here uh, we we see that a clinical interpretation template for explaining the model's outputs. It helps frame the results in a way that is understandable for a medical AI context. The important part is that models should not be treated as replacement for clinicians. Instead, it can act as a support tool by providing predictions along with visual explanation. In the next section, we save the final results. This section mainly just saves the experiment summary, including the selected final model, test metrics, save checkpoints, and output paths. It is important because it makes the notebook reproducible and keep the final results organized after training and evaluation are complete. For our final output preparation, we see the next cell. Here, from here onward, the model prepares the final output for presentation and reporting. We are not retraining the models. These organize the existing results into clean figures, tables, and benchmark comparisons. Now we see the comparison between the MedMinst V2 benchmark. In this section, we compare our two trained models with benchmark results reported in the MedMinst paper. Our DenseNet 121 model achieved a macro AUC of 0.830, while our ResNet 18 baseline achieved about 0.819. We also include MedMinst V2 benchmark models such as ResNet 18 and 50, AutoKeras, and Google AutoML Vision. This comparison gives external context for our results. However, it should be interpreted carefully because our DenseNet 121 setup is exactly the same. It's not exactly the same as the official MedMinst V2 benchmark models. In the next section, we see the our core report ready figures. This section saves the main figures ready for the report and presentations. These include the res 18 versus dense 121 comparison, the dense 121 training curve, the MedMinst V2 benchmark comparison, and the confidence drop plot. In the next section 24, we see the GradCam and Ensemble Cam overlay example. This section saves the final XAI overlay example. Each figure shows three parts: the original chest mist image, the GradCam, and Ensemble Cam overlay. These saved examples are used for visually explaining how final DenseNet 121 model makes the predictions. They show which areas of X-ray contributed most to the predicted class. Next, we see our final figure index. This section creates a figure index for all final report ready figures. It lists each figure name, its file path, and a short description. This makes it easier to locate correct figure later for our report. And finally, this section generates our clean report ready tables. These include our model comparison table, the means V2 benchmark comparison, the selected model summary, DenseNet 121 class metrics, the XI confidence drop summary, and the selected XI example metadata. These output uh, makes everything organized and in markdown table formats. To conclude, DenseNet 121 was selected as the final model because it performed better than the ResNet 18 baseline. We also used GradCam, EnsembleCam, and confidence drop analysis to make the model more interpretable. The final notebook also saves all our models, figures, XI examples in an organized way, making our project reproducible for all. Thank you. This is all for me, and this concludes our project demonstration. If any of you two want to add something, please go ahead.
That's all, Tahsin. Thank you. Thank you, sir, for your time. And we end here. Thank you very much, sir.